First of all, I'd like to thank the organisers for inviting me for this virtual event. I would have liked to have met them in person and spent time with them, but unfortunately that's not going to happen. I'm going to make the most of this interesting workshop they've organised. We're decidedly in a new era of gravitational physics, and no one can deny that the LIGO discovery has been a real shot in the arm of general relativity. If you look back 10 years, this was definitely not the case, and you had to be brave and foolish to enter the field. Now, one of my colleagues has said that cosmology is a topic for old people, while gravitational waves is for the new. I sometimes feel that. So much of what we do now in cosmology is tied up with very technical work, tied to big collaborations. In some sense, all the low-hanging fruit has been picked. You could say that about gravitational waves as well. I mean, you shouldn't forget that gravitational wave physics have 50 years of focused work by some of the cleverest people. Yet the problems there have been hard and have taken up most of the attention. And as a result, there's much that still needs to or can be done and explained. I'll touch upon one such path, which curiously arises from the interplay between three arch topics of GR, cosmology, gravitational waves, and black holes. And I'm talking about this in a workshop on observational cosmology precisely because I think this is an interesting and unexpected route to constraining cosmological physics. And my starting point is the detection in 2017 of the coalescence of a binary neutron star. And if you recall, what we had then is we measured a binary neutron star merging and forming a black hole through various channels. Of course, we had the LIGO-Virgo detection that saw it come together and emit a burst of gravitational waves. But we also measured it in various wavelengths via what we now call, what we call electromagnetic counterparts. And basically, this picture shows two such examples of that with the Fermi satellite and with integral. And the net result of that is that we were able to measure some event at a distance of about 40 megaparsecs. And we measured two sources two detections, two sets of detections, a gravitational wave detection and an electromagnetic detection, which happened within a couple of seconds of each other. Now, if you think about this, this immediately allows us to work out something quite profound. If we know the distance that this object is at, it's about 40 megaparsecs. And if we know the speed at which the gravitational waves travel, we can work out how long it took to get to us. And so this is this TG that I'm writing over here. But we can do the same thing with the electromagnetic counterparts. We know the distance, it's 40 megaparsecs. It travels at the speed of light, and so the time that the electromagnetic waves took to travel us was TE. Okay? And we know that they arrived within a few seconds. So if we do TE minus TG, and so this here is TE, and this is TG, and we assume that the gravitational wave speed is the speed of light plus some small correction. We can Taylor expand this expression over here, and what we find is a constraint on this alpha, i.e. the difference, the deviation of gravitational wave speed from the speed of light. And we find that alpha is less than about 10 to the minus 15. It's microscopic. In other words, the speed of gravitational waves is almost exactly the speed of light. Now, this is fascinating. This is not something new in the sense that theoretically we know that in general relativity the speed of gravitational waves is the speed of light. But it turns out that we can do quite a lot with this simple result. And the place where we're going to use this is in exploring theories that go beyond general relativity. Let's just remind ourselves of what general relativity is. General relativity, we can encapsulate general relativity in the Einstein-Hilbert action, which I've written over here. And we have here the Planck mass, we have the Ricci scalar, and we have the metric. And from this we derive the Einstein field equations. Now, when we want to go beyond general relativity, inevitably, for a number of reasons that I'm not going to go into here, we need to add new degrees of freedom. And a notable and easy example of this is if this new degree of freedom is a scalar field. So one particular example of an extension to general relativity is if we make the Planck mass over here dynamical. Now this was an idea that was put forward by Pascual Jordan, Charles Brands, and Bob Dickey in the late 50s and early 1960s. And the action now looks like this. Your scalar field becomes your dynamical Planck mass, and there's a kinetic term for the scalar field. Okay? And so we've lost the Planck mass, and we've got this new degree of freedom. And this theory propagates a new degree of freedom and is different from general relativity. Now you can make this more complicated. And indeed, you can generalize these scalar tensor theories, that is, theories where you have a metric and a scalar field, to something much more elaborate. These theories, you've probably heard of them. You either know them as the Horndeski theory, the Horndeski action, or covariant Galileons. And the idea there is that you construct the most general action out of a metric and a scalar field, which have second-order equations of motion. So schematically, I've written this up here, where it's a function where in front of r, instead of just having phi now, I also have x, and x is nothing more than the kinetic energy of the scalar field. And then I can have other terms over here, which depend on phi, x, and even the second derivative, the box of phi. Okay. Now these theories are interesting because cosmologically they're interesting. In other words, you can construct such theories such that their energy density, or their fractional energy density, is of order 1. In other words, it's comparable to the energy density in the other matter components which are driving the expansion of the universe. And in particular, you can tune these theories so that they can drive the acceleration of the universe. In other words, these scalar fields can be responsible for the acceleration of the universe. These scalar fields can be the dark energy. In fact, the current main target for cosmological surveys is to figure out what the dark energy is. And this class of theories is one of the main candidates. So in some sense, these scalar fields are the dark energy, and they are a target for cosmological observations. But I'm going to go down a completely different route. When you look at these theories, something interesting happens. One of the things you can do is you can expand your metric around Minkowski spacetime and a small perturbation, and just look at the transverse traceless part of that. And the transverse traceless part of that, if you remember your undergraduate general relativity, is nothing more than gravitational waves. If you do that and you plug that into your scalar tensor action, you end up with an action for the perturbed metric over here, which looks like this. It basically looks just like a free scalar field, except with a speed of a propagation speed which could be different from the speed of light. In other words, you have this alpha, which I introduced before. Now, in the case of general relativity, where you don't have that phi, that c of g is simply the speed of light. In other words, alpha is 0. But that is not necessarily true in other scalar tensor theories. And here I'm going to construct a very simple example of where you can get a speed of gravitational waves which is different from the speed of light. Here I've, in front of r, instead of just having phi, I have phi and x, and I have this arbitrary function m squared. Okay? Let me just remind you that x is the kinetic energy in the scalar field. If you do the whole procedure of working out what the action for the gravitational waves are, you end up finding that alpha you can derive alpha in terms of derivatives of that function there and the function itself. And here I've written down the expression. Okay? And two things you note. If for alpha to be equal to 0, m squared mustn't depend on x. That's the first thing. But another thing is you can get alpha very close to 0 if the derivative of m squared with regards to ln x is much smaller than m. And you can show that that means that the scalar field has absolutely no effect cosmologically, in which another way of putting it is omega phi is much less than 1. And a way of thinking about it is that in the first case in A, that the gravitational waves don't really couple to the medium, the scalar field that you can think of this medium, this ether living out in space-time. But the second situation is if the medium is negligible. It's just so dilute that it has absolutely no effect on the propagation of the scalar fields. Okay? The converse of this is if it does depend on X and is appreciable, you will affect the propagation of gravitational waves. So now let's go back to GW170817. GW170817 showed that alpha is approximately 0. And if you look at the Horndeski action, what you find is that it reduces considerably. So, as we saw before, the bit in front of R loses a dependence on X. You're then allowed some jumble of phi and X over here, and then a specific combination of phi and X with box phi. And that is the scalar tensor action, the Horndeski action reduces to this. This is all you're allowed to play with. Now, this is a huge reduction in theory space. If I'd written the general Horndeski action, I would have filled this whole page. But now it's just become this little condensed thing over here. Now, I should mention that there are caveats to this. First of all, it turns out that the Horndeski action is not the most general scalar tensor theory with second-order equations of motion. And over recent years, we have found a method to construct theories with arbitrary derivatives that nevertheless give you only second-order equations of motion. These actions are known as the dosed actions. And we know a little bit about them, but we don't know a lot about them. So they're work in progress. The other thing is we have to be careful. All of these theories are, in some sense, effective field theories. And it's been argued that by applying the GW170817 constraint to this theory, we're beyond the range of validity of the effective field theory that describes these actions. So all of these things one has to take into consideration. But for now, I'm just going to assume that no, it holds. This constraint that we find means that the only scalar tensor theories that we can work with are these. And I'm going to explain why this is useful, and I'm going to come back to these caveats in a bit. Now, I've spoken about cosmology and gravitational waves. Now I'm going to talk about black hole. And the first thing I'm going to bring up is the fact that in general relativity, black holes are uniquely described in terms of Schwarzschild or Kerr. This is known as the no-hair theorem. In other words, black holes are uniquely described in terms of their mass and their spin. Now, beyond general relativity, this is not necessarily the case. If you think about it, in scalar tensor theories, you've got this extra degree of freedom, you've got this phi field, and this phi field will depend on R, and if this phi field couples to matter, this will manifest itself as a fifth force. Not only that, this phi field can source the Einstein field equations and affect the Einstein field equations, and so the metric can be different from Schwarzschild. So it's not necessarily true that in scalar tensor theories, black holes, the black hole no-hair theorem is satisfied. You may have hairy black holes. Now, it turns out that if you look at the most basic theory, the one that I presented before, the Brans-Dicke gravity, which I've rewritten over here, it indeed has no hair. In other words, the space-time is described by Schwarzschild, and the scalar field is a constant. And this is a result that's been known for almost 50 years. Stephen Hawking wrote one of the first clearest papers on this topic. On the other hand, over the years, we've constructed more and more elaborate scalar tensor theories. And recently, a proposal was made where you can take Brans-Dicke theory, and then you couple your scalar field to the Gauss-Bonnet invariant. What you find is that there you can get a hairy black hole. What does this mean? This means that the Schwarzschild bit now is corrected, and you get an extra new bit, which is driven by something which is the scalar charge, which you can derive from the scalar field. And not only that, the scalar field is not a constant anymore. It has a 1 over r term and a 1 over r squared term. In other words, it works very much like a fifth force. So the Einstein-Dilaton Gauss-Bonnet is a good counterexample of a scalar tensor theory where you can get hair. So where do we find ourselves? Well, it's very interesting. If we restrict ourselves to the Horndeski theories which satisfy the GW170817 constraint, that is, theories which have an appreciable effect on the expansion of the universe, in other words, have cosmological significance, i.e. could be the dark energy, or to put it yet another way, in which omega phi is close to 1 or some fraction of it, then you can't. Circumstantial evidence shows that all black holes have no hair in this theorem. In other words, if omega phi is close to 1, then the GW170817 constraint implies that black holes have no hair. What do I mean by circumstantial evidence? I mean by circumstantial evidence that if you look at all the sub-no-hair theorems applied to scalar tensor theories, and you look at all the attempts to construct examples of theories with hair, none of these theories pass the GW170817 constraint. In other words, the only theories that pass the constraint have the black holes have no hair. I recall that in just the previous slide, I showed you the Einstein-Dilaton-Gauss-Bonnet theory, and that had hair. But in that case, it has no cosmological impact. You can show that omega phi is much, much less than 1. The same is true about another theory that is often studied by relativists, the Chern-Simons theory. Again, it has no cosmological impact. Now, as I mentioned, the dosed theories, the higher derivative theories, they may have hair, but that is still work in progress. So, the statement is that if you want your field to have a cosmological impact and satisfy the GW1708-817 constraint, black holes will have no hair. But then this is a problem, because if you remember, the beginning of this is I'm going to try and use black hole Ringdown to constrain dark energy. And I'm saying here that the only theories of dark energy viable by GW170817 constraint will have no hair. So how can I use black holes to test for them? There are going to be no fifth forces, so we can't use the standard PPN constraints. There are going to be no effect on orbits passing by black holes, and there's going to be no effect on mergers and gravitational waves. So it seems like there's really no hope about using black holes to study these theories. Well, it turns out that there is, and it's something that we've come to realize only in the past few years. This is my schematic of a gravitational wave of a black hole binary merger. If you remember, and you should all know this by now because you've seen it so many times, the black holes orbit each other, they inspiral, they merge, and then they ring down, they settle down to a final state. And you have these three distinct parts in the gravitational waveform. You've got the inspiral, the merger, and the ring down. And I put here the data of the first one, the highest signal to noise one. And this tail part is the bit that I'm going to focus on, the ring down. Now, the ring down is quite interesting. The ring down, what do you do in the ring down? The ring down, you think about this as a perturbed black hole which wobbles and settles down to its final state. And again, as I said, we're looking at no-hair theorems, so we're only going to actually think about Schwarzschild black holes. The final state is going to be a Schwarzschild black hole. These perturbations, what are they? They're gravitational waves. But these gravitational waves have a particular feature. If you look at their boundary conditions, they're infalling into the black hole horizon because nothing can come out of the horizon, and they're outgoing towards infinity because they're sourced by the black hole. We're not sending anything in. Now, this is very interesting because this is a boundary value problem, but it's an unconventional boundary value problem. This is not like the normal modes problems you did in undergraduate math. What you find here is that, as with normal modes, you find a discrete set of frequencies, but these frequencies are not real, they're complex. In other words, what you find is a set of waves which are damped, exponentially damped. The frequency, the complex frequency not only tells you the oscillation frequency, but the damping time as well. These are known as quasi-normal modes. Now, these quasi-normal modes are fascinating because if you're working in general relativity, these quasi-normal modes contain a lot of information about your black hole spacetime. In particular, there's this. I'm not going to use this disparagingly. It's just something that people have adopted. Quasi-normal modes satisfy a no-hair theorem. In other words, the quasi-normal mode frequencies are uniquely determined by the mass and the spin of the black hole. So in this plot, what I'm showing you here is on the x-axis, I've got the real part of the quasi-normal modes suitably normalized by the mass, and on the y-axis, I've got the imaginary part. And what you have is these are quasi-normal modes. If you remember, you're decomposing a wave. You're going to have the n, the fundamental number, then L and M are the spherical harmonic numbers or spheroidal harmonic numbers. In this case, it's spherical harmonic numbers, spheroidal harmonic numbers. Sorry. And these, if you consider no spin, you will have these dots here, which I'm just crossing here, okay? And if you vary the spin, for each case, you'll get these lines, okay? But the important thing to note is that you have these completely localized tracks in frequency space. Not only that, these tracks are uniquely determined by M and J. In other words, if you can measure 3 quasi-normal mode frequencies, or if you can measure 3 quasi-normal mode frequencies, you can, well, if you measure 2 quasi-normal mode frequencies, you can measure the mass and the spin of the black hole. Not only that, if you measure 2 quasi-normal mode frequencies, you can determine the mass and the spin of the black hole and predict what any other of the quasi-normal mode frequencies are. So it's a beautiful consistency test for Schwarzschild black holes or black holes in general relativity. Now, the folklore is that this is true in any theory. That if you do this, if you're doing this on Schwarzschild, you'll always find this relationship. But it turns out that this isn't necessarily true. And to do that, we need to look at the equations from which these quasi-normal modes come. So let me remind you, we're solving gravitational waves and scalar field perturbations on this black hole spacetime, okay? So delta phi is your scalar field perturbation and h is your gravitational wave perturbation. And these are PDEs, but I'm just going to separate out e to the I omega t and just plug that in. And if you do that, you end up with 2 Schrödinger-like equations over here. Now, if you're doing general relativity, what you find is that you find just the first equation here, and this bit over here is equal to 0. And that's where you get those quasi-normal modes that I put on the previous page. But if you have a scalar field which is non-minimally coupled to the metric, you'll be sourced by fluctuations in the scalar field. And the scalar field will satisfy its own quasi-normal mode equation, its own Schrödinger-like equation. And the Schrödinger-like equation will have a potential, and this potential will depend on parameters in the action. They'll depend on it in a particular way. It turns out that the dependence is on one constant, which is in some sense an effective mass of the scalar field perturbation, which you can derive from the action. But the key thing here to note is you can solve for the quasi-normal modes of the scalar field here. You find this quasi-normal modes. And then you plug these solutions back up here. And then you solve for this equation, and you solve for the homogeneous part of this equation, which will give you the original general relativistic quasi-normal modes. But then you'll get some new quasi-normal modes. So you'll get a new set of quasi-normal modes on top of the original quasi-normal modes that you had from general relativity. What this means is that the quasi-normal mode no-hair theorem isn't really true anymore. In other words, if you measure quasi-normal modes, by just measuring M and J, you won't be able to predict all of the other quasi-normal modes, because there'll be other quasi-normal modes which will depend on this parameter mu, which is a function of the scalar field action. Now, what does this mean in practice? Well, let's assume that this psi is excited somehow, and it has an amplitude AS, a scalar, amplitude scalar, all right? What I have here is 3 plots illustrating the impact of that scalar field fluctuation on the metric, on the gravitational wave. And so if you look at it, the blue line is what you would get if you had no scalar field, okay? And now the red line is if you now add the scalar field fluctuation to you contaminate the gravitational wave by the scalar field fluctuation. And on the left panel, I start off with a very small amplitude of only 10%, and you see that it's, there is a little bit of an effect, but it's more indistinguishable. It's almost indistinguishable, but there is an effect there. If I divided those 2 curves, you would see an effect. If the amplitude of the scalar field relative to the amplitude of the gravitational wave was 50%, well, then you really start to see a distortion of the gravitational wave as a function of time, of the Ringdown. This is actually a plot of the Ringdown. And if the amplitude of the scalar field is the same as the gravitational wave, then you really see severe distortions. Now, this is a highly idealized case. This is not what we're looking for. We'll be looking for something more like that or even smaller. So the question is, for small AS's, can we pick up the effect of the scalar modes in the Ringdown? Okay. Now this is an attempt to answer that question. Okay, so here what I have is, let me deconstruct all this. Rho is the signal to noise of the gravitational wave detection given some gravitational wave noise. Okay, mass is that mu squared. That mu squared is the mass. I've got it over here, and I've just written it now just so you can see explicitly how it depends on the action, the reduced action that resulted from GW170817. Okay, so this is the thing we're looking for. We want to put constraints on this object over here. All right. So this is assuming like a LISA, a particular setup with LISA. On the x-axis, I've got the mass of the black hole, of the final black hole over here. And on the y-axis, I've got the amplitude of the scalar field. Okay, the amplitude of the scalar field relative to the gravitational wave. And look, I'm going down from 1. So this is 10 to the minus 1, this is 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. And then the color is basically the signal to noise here times the mass of the scalar field that we can detect at 5 sigma times in the appropriate units. And what we find is that for very large masses here and for very large amplitudes, we can go down to 10 to the minus 18, which is remarkable. We can really constrain ultralight scalar, ultralight corrections, or very small. Let's get the mass of the effective mass of the scalar field can be really small, and we will be able to detect it. But these are very large black holes. If we move over here and go to 10 to the minus 6, and and we go to 10 to the we go to the typical supermassive black holes over here, and we look at amplitudes in the scalar field which are of order 1%, we're still probing quite small values of the mass over here. In other words, it should be possible with LISA to pick up or to scan some range of parameters for this action using Ringdown, black hole Ringdown. So this is promising, right? This is promising. This means that we can use black holes Ringdown to do cosmology. Now there's a point here which is probably puzzling some of you, which is the following. I've said that black holes have no hair in these theories, right? So imagine that you have some black holes sitting there and who come together. They have no scalar field profile. And as they come together, they have no scalar field profile, and they merge and they end. Where are we going to get perturbations to the scalar field profile? The equations for the scalar field are homogeneous. I've got them over here. There's nothing here which will excite psi. In other words, if you start off with psi equals 0, you are going to end up with psi equals 0. So how are we going to excite these psi? How are we going to get the AS which we needed to be able to make statements about the detectability or the constrainability of these theories? And that's really the challenge. And it's a challenge that I open up to you because I think it's something that we should be looking for. Now, the first thing I'm going to say is there are many assumptions behind no-hair theorems. The no-hair theorems are very restrictive. They assume stationarity, they assume asymptotic flatness. A particular example of how you might excite the scalar field, which I'm not going to go into now, but I should mention, is via superradiance, where you basically generate long-lived hair. And the idea there is to build on an idea by Roger Penrose that you can extract energy and angular momentum from a Kerr black hole. He has these beautiful papers on what's known as the Penrose process. Now, if you extend this idea from particles to fields, you can see that you can generate quantum fluctuations in the scalar field. Fluctuations in the scalar field will be amplified to form scalar field clouds. And it'll have the effect of forming black hole hair, long-lived black hole hair. You can even construct black hole bombs from a particular positive feedback. So this is one way. But we're talking about cosmology. The focus of this workshop is cosmology. So I'm going to bring up something else which has been overlooked. So what's another way we could generate these black hole fluctuations? If you look at the equation of motion, the simplest equation of motion for a scalar field, which is the Klein-Gordon equation, you've got a mass term here, all right? And if you solve this asymptotically, if you solve this in the regime where space is homogeneous, you get rid of all the gradients, and you just end up with a harmonic oscillator equation, which you can solve, and it's cosine mt. Now, to you cosmologists, this is well known. This is the idea behind using a massive scalar field as an axion. If you work out what the equation, what the energy density is, and you work out what the pressure is, you find that it behaves as pressureless matter, and so rho phi behaves as 1 over a cubed. In other words, axions can be the dark matter. Now, what is interesting is this is the general boundary condition for a massive scalar field. It's cosine mt. But that means that if you have a scalar tensor theory with a scalar field where you have this effective mass, it's going to have non-trivial boundary conditions. You can't make it asymptotically flat, nor can you make it stationary, because the scalar field energy density goes as 1 over a cubed, and it oscillates. And we've shown that this plays a crucial role. If you immerse a black hole in a homogeneous oscillating scalar field, which is the general solution of a Klein-Gordon equation on a homogeneous background, you'll get black hole accretion. And this is just one particular nice plot showing this. This I've done now with a Kerr black hole. What you find is that you get this gradual accretion of the scalar field around the black hole. So just because of the cosmological boundary conditions, and that cosmological boundary conditions are not asymptotically flat nor stationary, you expect scalar fields to accrete around Kerr. And if they accrete around Kerr, you have your conditions to generate your AS. Now, this is one particular example that we're exploring in some detail, but you can kind of generalize this and think about where could you get this AS more generally. I'm focusing on black hole mergers, but we are expecting to measure neutron star mergers, or binary or black hole and neutron star mergers. We know that neutron stars can support fifth forces. Neutron stars aren't subjected to no hair theorem, so you expect to have hair, you expect to have non-trivial profiles of the scalar field. So if you have a scalar field coming to two neutron stars coming together, the scalar field will be this tangled mess. The neutron stars will combine, form a black hole, and the final black hole will have to shed its scalar field somehow, and this will be the scalar field perturbations that then can mix with the gravitational waves. You go and look for those quasi-normal modes. But why stop there? These are scalar fields. These are energetic bodies. They can form black holes themselves. For example, you can construct boson stars of these scalar fields, which eventually collapse. And when they collapse, again, the final black hole, because of what I told you, will have to have no hair. But these were made of scalar fields. It's got to get rid of its scalar field somehow. This will contaminate the quasi-normal modes, and you can go and look for these frequencies. An even more exotic example, and a topic in which many of us worked on many decades ago, is topological defects. If you have a U1 symmetry, for example, you will form cosmic strings. If you look at a cosmic string loop, the cosmic string loop will collapse. It'll collapse, it'll pass its own event horizon, it'll form a black hole, it's got to shed all its energy, it's got to shed its scalar field, it'll contaminate the quasi-normal mode spectrum. So this is, in some sense, the theme, or one of the things we were asked to is a forward-looking part to our talks. I will fold it into the conclusion. My point is, unusually or unexpectedly, I'm proposing that we use Ringdown to look for cosmological scalar fields. In other words, to constrain dark energy. This is not something that people have thought about before, and I think is there's a really clear path where all the steps are easy to calculate. There are two things that need to be done. First of all, there's a fair amount of work on the data analysis and how we accurately measure the quasi-normal mode frequencies. The quasi-normal mode frequencies are not a complete basis, so it's not clear how you're going to match the quasi-normal mode frequency wave basis to the data. Not only that, the quasi-normal mode frequencies arise in linear perturbation, but black holes mergers are hugely nonlinear. So where do you cut the data so you're accurately only extracting the quasi-normal mode frequency? There are all these interesting data analysis aspects that people should look at, and what I found is that these are topics that even a cosmologist can look at. You do not need to be incredibly well versed in gravitational wave data analysis to understand what the issues are or thinking about them. These are time series that we can know how to work with. But even more importantly, for theorists, is what are the possible sources of these scalar modes around black holes, around the final black holes? In other words, where do we get the ASs? I've told you about accreting scalar fields because of cosmological boundary conditions. I mentioned superradiance. I mentioned boson stars, cosmic strings. All of this has to be worked out in detail, but I bet there are even more examples that if people thought about more carefully, they'd come up with more examples, more sources of these scalar fluctuations around scalar fields.